I have this matrix A here that I want to put into reduced row echelon form. And we've done this multiple times. You just perform a bunch of row operations. But what I want to show you in this video is that those row operations are equivalent to linear transformations on the column vectors of A. So let me show you by example. So if we just want to put A into reduced row echelon form, the first step that we might want to do if we want to zero out these entries right here is, let me do it right here, is we'll keep our first entry the same. So for each of these column vectors, we're going to keep the first entry the same. So there's going to be 1, minus 1, minus 1. And actually, let me simultaneously construct my transformation. So I'm saying that my row operation I'm going to perform is equivalent to a linear transformation on the column vector. So it's going to be a transformation that's going to take some column vector, a1, a2, and a3. So it's going to take each of these and then do something to them. And do something to them in a linear way. They'll be linear transformations. So we're keeping the first entry of our column vector the same. So this is just going to be a1. It's just going to be a1. This is a line right here. That's going to be a1. Now, what could we do if we want to get to reduced row echelon form? We'd want to make this equal to a 0. So when we want to replace our second row with the second row plus the first row, because then these guys would turn out to be 0. So let me write that in my transformation. I'm going to replace the second row with the second row plus the first row. With the second row plus the first row. And let me write it out here. Minus 1 plus 1 is 0. 2 plus minus 1 is 1. 3 plus minus 1 is 2. Now, we also want to get a 0 here. So let me replace my third row with my third row minus my first row. So I'm going to replace my third row with my third row minus my first row. So 1 minus 1 is 0. 1 minus minus 1 is 2. 4 minus minus 1 is 5. Just like that. So you see, this was just a linear transformation. And any linear transformation you could actually represent as a matrix vector product. So for example, this transformation, I could represent it, to figure out its transformation matrix, if we say that T of x is equal to, I don't know, let's call it some matrix S times x. We already used the matrix A, so I have to pick another letter. So how do we find S? Well, we just apply the transformation to all of the column vectors, or the standard basis vectors, of the identity matrix. So let's do that. So the identity matrix, I'll draw it really small like this. The identity matrix looks like this: 1, 0, 0, 0, 1, 0, 0, 0, 1. That's what the identity matrix looks like. To find the transformation matrix, we just apply this guy to each of the column vectors of this. So what do we get? Do it a little bit bigger. So the first, we apply it to each of these column vectors, but we see the first row always stays the same. So the first row is always going to be the same thing. So 1, 0, 0. I'm essentially applying it simultaneously to each of these column vectors, saying, look, when you transform each of these column vectors, their first entry stays the same. The second entry becomes the second entry plus the first entry. So 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. And then the third entry gets replaced with the third entry minus the first entry. So 0 minus 1 is minus 1. 0 minus 0 is 0. And then 1 minus 0 is 1. Now notice, when I applied this transformation to the column vectors of our identity matrix, I essentially just performed those same row operations that I did up there. I performed those exact same row operations on this identity matrix. But we know that this is actually the transformation matrix, that if we multiply it by each of these column vectors, or by each of these column vectors, we're going to get these column vectors. So you could view it this way. Let me call this is right here, this is equal to S. This is our transformation matrix. So if we could say that S, if we create a new matrix whose columns are S times this column vector, S times 1 minus 1, 1, and then the next column is S times, I wanted to do it in that other color, S times this guy, minus 1, 2, 1. And then the third column is going to be S times s times this third column vector, minus 1, 3, 4. This product, we now know we're applying this transformation. This is S times each of these column vectors. That is the matrix representation of this transformation. This guy right here, this guy will be transformed to this right here. That'll become, let me do it down. Let me do it down here. This guy, I wanted to show that stuff that I had above here as well. Well, I'll just draw an arrow. That's probably the simplest thing. This matrix right here will become that matrix right there. So another way you could write it, this is equivalent to what? What is this equivalent to? When you take a matrix and you multiply it times each of the column vectors, when you transform each of the column vectors by this matrix. This is the definition of a matrix-matrix product. This is equal to our matrix S. I'll do it in pink. This is equal to our matrix S, which is 1, 0, 0, 1, 1, 0, minus 1, 0, 1, times our matrix A, times 1, minus 1, 1, minus 1, 2, 1, minus 1, 3, 4. So let me make this very clear. This is our matrix, this is our transformation matrix S. This is our matrix A. And when you perform this product, you're going to get this guy right over here. You're going to get this guy right over here. Let me just copy and paste it. Edit. Let me copy. And let me paste it. You're going to get that guy. Just like that. Now, the whole reason why I'm doing that is just to remind you that when we perform each of these row operations, we're just multiplying. We're performing a linear transformation on each of these columns, and it is completely equivalent to just multiplying this guy by some matrix S. In this case, we took the trouble of figuring out what that matrix S is. But any of these row operations that we've been doing, you can always represent them by a matrix multiplication. You can always represent them by a matrix multiplication. So this leads to a very interesting idea. When you put something in reduced row echelon form, let me do it up here. So let's just finish what we started with this guy. Let's put this guy in reduced row echelon form. So this, we already said, this is equal to, let me call this first S. Let's call that S1. So this guy right here is equal to that first S1 times A. We already showed that that's true. Now let's perform another transformation. Or let's just do another set of row operations to get us to reduced row echelon form. So let's keep our middle row the same, 0, 1, 2. And let's replace the first row with the first row plus the second row, because I want to make this a 0. So 1 plus 0 is 1. Let me do it in another color. 1 plus 0 is 1. Minus 1 plus 1 is 0. Minus 1 plus 2 is 1. Now, I want to replace the third row with, let's say the third row minus 2 times the first row. Third row minus 2 times the first row. So that's 0 minus 2 times 0 is 0. 2 minus 2 times 1 is 0. 5 minus 2 times 2 is 1. 5 minus 4 is 1. And we're almost there. We just have to zero out these guys right there. See if we can get this into reduced row echelon form. So what is this? I just performed another linear transformation. And actually, let me write this. Let's say if this was our first linear transformation, what I just did is I performed another linear transformation, T2. I'll write in a different notation, where you give me some vector, some column vector, x1, x2, x3. What did I just do? What was the transformation that I just performed? My new vector, I made the top row equal to the top row plus the second row. So that's x1 plus x2. I kept the second row the same. And then the third row, I replaced it with the third row minus 2 times the second row. That was a linear transformation we just did. And we could represent this linear transformation as being, we could say T2 applied to some vector x is equal to some transformation vector S2 times our vector x. Now, we could say that this is equal to, we could say, because if we applied this transformation matrix to each of these columns, it's equivalent to multiplying this guy by this transformation matrix. So you could say that this guy right here, we haven't figured out what this is, but I think you get the idea. this matrix right here is going to be equal to this guy. It's going to be equal to S2 times this guy. And what is this guy right here? Well, this guy is equal to S1 times A. So it's going to be S2 times S1 times A. Fair enough. So this is just S2 times S1 times A. And you could have gotten straight here if you created a new, if you just multiplied S2 times S1. This could be some other matrix, and you just multiplied it by A. You'd go straight from there to there. Fair enough. Now, we still haven't gotten this guy in reduced row echelon form. So let's try to get there. And I've run out of space below him, so I'm going to have to go up. So let's go upwards. Let's go upwards like this. And what I want to do is I'm going to keep the third row the same. Keep the third row the same, 0, 0, 1. And let me replace the second row with the second row minus 2 times the third row. So we get a 0, we get a 1 minus 2 times 0, and we get a 2 minus 2 times 1, so that's a 0. And let's replace the first row with the first row minus the third row. So 1 minus 0 is 1, 0 minus 0 is 0, and 1 minus 1 is 0. Just like that. And since we did them for the, let's just actually write what our transformation was. Let's call it T3. I'll do it in purple. T3 is the transformation on some vector x. Let me write it like this. On some vector x1, x2, x3. It was equal to, what did we do? We replaced the first row with the first row minus the third row. x1 minus x3. We replaced the second row with the second row minus 2 times the third row. So it's x2 minus 2 times x3. And then the third row just stayed the same. So obviously, this could also be represented. This could also be represented. T3 of x could be equal to some other transformation matrix, S3 times x. So this transformation, when you multiply it to each of these columns, is equivalent to multiplying this guy times this transformation matrix, which we haven't found yet. But we can write it. So this is going to be equal to S3 times this matrix right here, which is S2, S2, S1, A. And what do we have here? We got the identity matrix. We put it in reduced row echelon form. We got the identity matrix. And we already know from previous videos, if the reduced row echelon form of something is the identity matrix, then we are dealing with an invertible transformation or an invertible matrix. Because this obviously could be the transformation for some transformation. Let's just call this transformation, I don't know, let's just call it T. Did I already use T? Well, let's just call it T naught for our transformation. Applied to some vector x, it might be equal to ax. So we know that this is invertible because we put it in reduced row echelon form. We put its transformation matrix in reduced row echelon form, and we got the identity matrix. So that tells us that's an invertible. But something even more interesting happened. We got here by performing some row operations, and we said those row operations were completely equivalent to multiplying this guy right here by multiplying our original transformation matrix by a series of transformation matrices that represent our row operations. And when we multiplied all this, this was equal to the identity matrix. Now, in the last video, we said that the inverse matrix, so if this is T naught inverse could be represented. It's also a linear transformation. It can be represented by some inverse matrix that we just called A inverse times x. And we saw that A inverse times, or the inverse transformation matrix times our transformation matrix is equal to the identity matrix. We saw this last time. We proved this to you. Now, something very interesting here. We have a series of matrix products times this guy that also got me the identity matrix. So this guy right here, the series of matrix products, this must be the same thing as my inverse matrix, as my inverse transformation matrix. And so we could actually calculate if we wanted to. We could actually, just like we did, we've actually figured out what S1 was. We did it down here. We could do a similar operation to figure out what S2 was, S3 was, and then multiply them all out, and we would have actually constructed A inverse. But something, I guess, something more interesting we could do instead of doing that. What if we started off what if we applied these same matrix products to the identity matrix? So the whole time we did here, when we did our first row operation, so we have the matrix A, and let's say we have an identity matrix on the right. Let's call that I right there. Now our first linear transformation we saw that right here. That was equivalent to multiplying S1 times A, right? The first set of row operations was this. It got us here. Now, if we perform that same set of row operations on the identity matrix, what are we going to get? We're going to get the matrix S1. S1 times the identity matrix is just S1. All of the columns of anything times the identity times the standard basis columns, will just be equal to themselves, and you'll just be left with that S1. Or you could call this as S1 times I, but that's just S1. Fair enough. Now you performed your next row operation, and you ended up with S2 times S1 times A. Now if you perform that same row operation on this guy right there, what would you have? You would have S2 times S1 times the identity matrix. Now, our last row operation we represented with the matrix product S3, or multiplying it by the transformation matrix S3. So if you did that, if you have S3, S2, S1A, but if you perform the same exact row operations on this guy right here, you have S3, S2, S1 times the identity matrix. Now, when you did this, when you performed these row operations here, this got you to the identity matrix. But what are these going to get you to? This is when you just perform the same exact row operations you perform on A to get to the identity matrix. If you perform those same exact row operations on the identity matrix, what do you get? Well, you get this guy right here. Right? Anything times the identity matrix is going to be equal to itself. So what is that right there? That is A inverse. That is A inverse. So we have a generalized way of figuring out the inverse for a transformation matrix. What I can do is, let's say I have some transformation matrix A. I can set up an augmented matrix where I put the identity matrix right there, just like that. And I perform a bunch of row operations. And you could represent them as matrix products, but you perform a bunch of row operations on all of them. You perform the same row operations you perform on A as you would do on the identity matrix. And by the time you have A as an identity matrix, you have A in reduced row echelon form. At the time A is like that, your identity matrix is going to, having performed the same exact operations on it, it is going to be transformed into A's inverse. And this is a very useful tool for solving actual inverses. Now, I've explained kind of the theoretical reason why this works. In the next video, we'll actually solve this. Maybe we'll do it for the example that I started off with in this video.